Start recording. Okay, so I think I've got the recording on. I think I've got the microphone on. You guys can all hear me okay? Okay, cool. So, yeah, I don't know why this didn't record the sound last week. Um, you test something before and it works, then when the real thing happens, it stops working. I don't know. But at least now when I'm talking, the little microphone bar is going up and down. So hopefully that means the microphone will work this time. We will see. So today I want to go over um, some more detail about how the computer represents numbers as bit patterns and stuff like that. So we'll go into how computers count numerically and a couple of ways that data gets represented and interpreted. Before I do that, any questions on the stuff from Tuesday? Basically, the description of the algorithms and what they are and how they work, and the introduction to bits and bytes and that kind of thing. That's kind of where we should be at right now. So far, so good? All right. All right. So here's where we're at. And so stop me if this is not something that you're cool with. Computers store data as electrical zeros and ones. A single 0 or 1 is a bit. 8 bits makes a byte. And so the way to get, well, I shouldn't say the way, I should say the meaning of a given byte, what the zeros and ones mean, depends on the context. And by the context, I mean the situation you're using it for. Whatever program or whatever part of the computer is using it can store those bits and interpret them in different ways. So it's very possible, even likely, that the exact same sequence of zeros and ones could mean different things based on what context, what situation we are talking about with how to interpret it. Okay, so one interpretation one byte is equal to one printable character. So one way to interpret 8 bits, so that's 8 bits, is as some way of storing letters or numbers or digits or something like that. So there exists I guess I'll call it a standard translation of bits to characters called ASCII, which is pronounced ASCII. And that's just a giant table that maps bit patterns to letters or characters or symbols. So it actually turns out this bit pattern is capital A. There's a different bit pattern for lowercase a. There's a different bit pattern for the digit. So all single characters. In other words, anything you can type on a keyboard have their own ASCII combination. And so letters have ASCII combinations, lowercase letters have ASCII combinations, single digits are things you can type on a keyboard and have ASCII combinations. Symbols have ASCII combinations. I don't know how to write this, but the space, like the space bar space, is a symbol that has an ASCII combination. So there's a giant thing called the ASCII table. Shows all of the combinations of representations of characters. So let's see if this works. If you just type into a search engine ASCII table, ASCII-table, you'll get a whole bunch of results. I'm going to try to share one with you here. We'll see how this works. Screen share. Oh no, don't beach ball me. You guys see this web page that came up? So hopefully you can see that I put up a web page, and the columns you want to look at are this column with all of the zeros and ones in it, and the column next to it that has a symbol. Can you guys see this? Okay. So what you're seeing, and I never, ever, ever want you to have to memorize this at all, because oh my God. Okay. What I want you to see though is that every single letter has a bit pattern in this table. Every single lowercase letter has a bit pattern in this table. All of the printable symbols, and some weirdo symbols like, the cent sign and the pound sign and stuff like that have symbols. And then even, it's like way up here, weird stuff like, I don't even know what some of these things mean. I was looking at the other day. Backspace has an ASCII symbol. End of transmission has a ASCII symbol. So even things that are not necessarily printable characters, the escape character has an ASCII symbol. Okay, so this is just a table, and just how do they decide which bit patterns map to which symbols? I don't know. They made something up. Okay, so one way to interpret bits is to look at a chart like this and see what it maps to and what printable character it maps to. Okay, so that's one interpretation. So let me bring back this thingy. But another more common interpretation is to think of a bit pattern as a number. So here's the thing. If all you have to count with is zeros and ones, right? Then, so in regular math, we count 0 as the smallest thing, that's not negative. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 11, 12, da, da, da. In our regular math, we have 10 different symbols that can be used to fill up every single position. right? 0, 1, 2, 3, 5, 7, 9, or 10 different things. If all I have is zeros and ones, then I can start with 0, and then I can say 1, but I can't say 2 because I don't have a 2. I just have zeros and ones. So the next thing that happens is this. Okay, just like when I ran out of symbols here, I rolled over the ones place back to 0 and added a 1 in the next column, which in regular math is the tens place. Here I go 0, 1, roll over the ones place, put a 1 in the next spot, that's 2, and then that's 3. And then for 4, I roll over this one, and then I have to roll over this one, and I go over there. Okay? And then 5, and then 6, and then 7, and then 8, and on we go. Okay? So what you're seeing is that when you can do it, right? You can count with just zeros and ones. You just end up using a lot more positions a lot faster because you don't have digits like 2 and 3 and 4 and 9 and stuff like that to go. Okay? So these numbers are regular numbers, but they're also called decimal numbers. Decimal means 10. And we have 10 different possible values for every single position in a number, right? These are called binary numbers because binary means 2, and there's only 2 possible values in every single spot. Okay, so I don't know if you guys had to do this in like elementary school or something like that, but if somebody writes the number 23,456, the way to think about that number and the way to break that number down is you say, I have 2 10,000s. I have 3 thousands. I have 4 hundreds. I have 5 tens, and I have 6 ones, right? Another way of saying this is I have 6 times 1 in the ones place. I have 5 times 10, which will get me my tens place. I have 4 hundreds. I have 3 thousands. I have 2 10,000s, right? And if you add those all up, you get back 23,456, right? And so the reason the places go up, ones, tens, hundreds, thousands, 10,000s, is because each one of these is 10 times the place before it. The tens place is 10 ones. The hundreds place is 10 tens. The thousands place is 10 hundreds. Okay? And on and on and on. So the reason I'm bringing this up is because in a binary number system, where all I have is zeros and ones, the positions, so that's this guy here is my ones place, right? The positions, instead of going up by tens, go up by twos. Binary means 2, okay? And so I have 1, 2. And I have 0, so that's the 2. I have 0 4s, 2 times 2. And I have 1 8, 2 times 4. And I have 1 16, 2 times 8. I have 0 32s, and I'm running out of room, 1 64. Okay? So the way I write these things down is, especially if you give me an 8-bit thing, okay? Well, before I do that, if you give me a decimal number, 19,463, that's my ones place. I'll mark the positions like this. That's my tens place. That's my hundreds place. That's my thousands place. That's my 10,000s place, and on and on and on it goes, right? If you give me a bit pattern, that's my ones place, that's my twos place, that's my fours place, that's my eights place, that's my 16s place. See how they double? That's my 32s, that's my 64s, that's my 128s, okay? So every single position in a binary number also holds larger and larger values. The difference is those larger and larger values go up by 2s in each position instead of by 10s, okay? So this means you can, well, this means there is an algorithm to turn a binary number into a decimal one. So algorithms like we did last time. Step one, find the, let's call it place value of each bit. And so this is the place value 1, this is the place value 2, all the way down across. Okay. Step 2, for each place value, if there is a 1, that place counts once. If there is a 0, that place, well, I'll say counts 0, but really doesn't count. Step 3. So add the place values of all places that have a 1. Okay, so here's an example of how to do that. I'm going to make this bigger, the exact same number, just bigger. And I'm using 8 bits here just because I think in terms of 8-bit bytes. This exact algorithm and formula will work for 3 bits or 9 bits or 80 bits or whatever you want. You just have more or less positions. Okay? So what I do is I walk through and I say you're the 1s place, you're the 2s place, you're the 4s place, you're the 8s place, you're the 16s place, you're the 64s place, you're the 120. What did I do wrong? Oh, I'm missing 32. Helps to be able to multiply. 32's place, 64's place, 128's place. And you're going to, with enough practice, know how to get these doubling numbers in your head pretty fast. So all of the positions that have a 1 are those. The 128, the 16, the 8, and the 4 all have 1s. And if you add those together, I start looking for ways to make common things that end in 0. So 16 plus 4 is 20. 128 plus 20 is 148. 148 plus 8 is 156. Okay. So you see how I did that? Any questions on that so far? You understand what the process is, what we're trying to do? Cool? Yes? Hello? Okay. All right. So I want you guys to do one. I'll make it a little smaller. So try that and kind of walk your way through the algorithm. Put the places of all the values in there, and see what you come up with. Anybody got anything? Anybody stuck and need help? 25. Yeah. Yep. Good. And so let me walk you through it just to, and I guess you can keep going. And that's 16 plus 8 plus 1, which adds up to 25, right? Anybody not get that? Anybody confused by what we're doing? Okay, the lab and the homework's going to be all about doing this kind of conversion-y stuff, okay? All right. So, that's binary to decimal. In the other direction, if I hand you a decimal number and you want to get a binary number out of it, there's two algorithms. Algorithm 1 is the books. It's slow, but always works. Step 1. Divide your decimal number by 2 and remember the remainder. So by remember, I just mean write it down someplace so that the remainders are going to end up being the bits here. Okay, so step 2, if your quotient, the thing you got when you divided, is not yet 0, go back to step 1. Step 3, if your quotient is 0, the remainders from bottom up define the bits from left to right. So here's an example of this. Okay, suppose I want to do, I don't know, 97. Wow, what did I just do? 96. iBooks, go away. Stop that. Stupid thing wants to update. 97, I said. Okay. 97. 97 divided by 2 is something. I probably should have picked a better example because I can't do 97 divided by 2 in my head. I think it's 47. 48. Remainder 1. 48 divided by 2 is 24, remainder 0. 24 divided by 2, keep going until your quotient 0, is 12, remainder 0. 12 divided by 2 is 6, remainder. See what I mean by slow? It's a lot of divisions. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, remainder, is 0, remainder 1. Okay? This is your binary number. 1, 1, 4 zeros, 1. And if you check it, it's always good to check your work and see if it goes back in the other direction. I should be able to do my binary to decimal algorithm and get back 97, right? That's the ones place, that's the twos place, 4, 8, 16, 32, 64, and 64 plus 32 plus 1 is 97. All right, so again, let's have you guys do, again, a smaller one. You guys do 11. Let's not do 11 because 11 looks like a binary number. Let's do 13. So give 13 a shot and see what you come up with. It'll have less digits than my 96 had, 97 had. So is it 110? I think you're missing a Z. Maybe, yeah. Oh, you're right. 8, 12, 13. So let's see. 13 divided by 2 is 6 with 1 left over. 6 divided by 2 is 3 with 1 left over. 3 divided by 2 is 1 with 1 left over. Oh, 6 divided by 2 has no remainder. Haha. 1 divided by 2 is 0 with 1 left over. 1, 1, 0, 1. And again, if you check your work by converting it back, 8 plus 4 plus 1 is 13. Ta-da. Make sense? Now you know why it's a Q course. It's the kind of thing you guys can all do. Maybe not super fast, but it's not the kind of thing you want to try to do for a million. You go from bottom to top, yeah. So this is left, and this is right. The reason why you go from bottom to top is your last thing is always going to be 1 divided by 2 is 0, remainder 1. And that's how it stops. And so you'll always have the 1 on the left, and that's the one, the first one you need to start the number. Okay. All right, so that's the algorithm that the book wants you to use. That's the algorithm that always works. Here, just to show you, Sean's faster algorithm that can mess you up if you're not careful. Step 1. Find the largest power of 2 less than or equal to your number. A power of 2 is 1, 2, 4, 8, 16, 32, 64, blah, blah, blah. Okay? Step 2, put a 1 in that place of the binary number and subtract the place value from your decimal number. Step 3, if the decimal number is greater than 0, go back to step 1. Step 4, if the decimal number is 0. You're done. Put zeros in all unfilled bits. So what this is doing is if you get a number like, well, no, I won't do 97 again. I'll do 43. Okay, it's not great with 43, but we'll see what happens. So whoa, what did I just do? The largest power of 2 less than or equal to 43. 1, 2, 4, 8, 16, 32. 64 is too big, so 32 is the biggest one less than it. So my answer is going to have all of these spots. A 1 spot, a 2 spot, a 4 spot, an 8 spot, a 16 spot, a 32 spot. And we're going to put a 1 in the 32 spot. We're going to subtract out 32 and get 11. Okay. Now, the largest power of 2 less than or equal to 11 is 8. So I have an 8. 11 minus 8 is 3. The largest power of 2 less than or equal to 3 is 2. 3 minus 2 is 1. The largest power of 2 less than or equal to 1 is 1. 1 minus 1 is 0. I'm done. Put zeros in all of the spots to the left. So this, to me, feels a lot like doing the binary number to decimal number conversion we did before backwards, right? Instead of adding the place values with all the ones, I'm putting ones in the place values and subtracting them from the number. That's the opposite of adding. The reason this screws people up sometimes is because if you count the powers of 2 wrong, if you forget that there's a 16 between 8 and 32, if you go 16 to 20 or something like that and don't do the doubling right, you get messed up. And if you pick a power of 2 that's too big, you get a negative. You don't want that. If you pick a power of 2 that's too small, you'll get too big of a number, and then I'll screw you up later. So I personally think this is faster. This is the kind of thing that I do when I do conversions in my head. If you prefer the first version, the slow, sure dividing version, go for it. I don't care. But I wanted to show you this just because when I do conversions, I'm going to probably do it this way so you know what I'm talking about. So just really fast, why don't you guys try to do 18? Okay. And try to do it this way if you can, or if you're not comfortable with it, do it the other way. That's fine too. But 18 I picked because it's pretty simple to do in this method. Any questions on what we're trying to make you do here? Looks like everybody's coming up with it. Yeah. So what's the biggest power of 2 less than 18? 16. So that's 1, 2, 4, 8, 16. Put a 1 in the 16 spot. Subtract out 16. You're left with 2. Hey, look at that. It's in 1. The biggest power of 2 less than or equal to 2 is 2. Boom, boom, boom. Okay? So both ways work. All right? So any questions on that? You guys more or less comfortable with what we're talking about, going back and forth between binary numbers and decimal numbers and all that? Sounds good? Okay. All right. So here's the next question. how many bits do I need to represent numbers? More than I need for a decimal number, right? 16, which is 2 digits, you guys told me was 5 different bits, right? So another way of asking this is, how many combinations are there with some number of bits? And before I do the bit thing, let me ask you this. How many combinations, in other words, let me ask it slightly differently. How many different numbers can I represent in decimal with 2 digits? And when I say 2, I really mean 2 or less, because I'm going to count that as a 2-digit number. Okay? So if I hand you 2 digits and I say how many different numbers are there with 2 digits, how many are there? Don't count them. 100, and I would count 0 because that is a valid 2-digit number, right? Make sense? So now let me go back to the bit question. If I have 2 bits, how many combinations do I have? 2 digits was 100. 2 bits, which when I can't have 5s and 7s and 9s and things like that, how many combinations do I have? 4. Why? Or I guess similarly, why 100? Yep, and there's only 2 possibilities for each number, so you can do it by listing them out. That's all 4 ways of doing it. Especially if I turn this ugly, stupid 6-looking thing into a 0. And so those are the 4 things I can do with 2 bits. The other way to think about it is 2 choices here, 2 choices here, and so that's 4 total. If I go to 3 bits, how many combinations? With 3 bits, 8. Because, well, one way to think about it is it's 2 times 2 times a third column of 2. Another way to think about it is I have all 4 2-bit things, and they can start with 0, or I have all 4 2-bit things, but they can start with 1. So it's twice as many things with 3 bits as there is with 2 bits. Okay? So in general, if I have n bits, where n is any number, I can represent 2 to the n combinations. 2 times 2 times 2 times 2. So remember, 2 to the n is 2 times 2 times 2 times 2 n times. Not to be confused with 2 times n, not to be confused with n squared, which is n on the bottom and 2 on the top. This is 2 times 2 times 2 times 2 times 2, n times. So 3 bits was 2 times 2 times 2, 3 times. 4 bits would be 2 times 2 times 2 times 2, 4 times, 16, and so on. Okay, 8 bits is 2 times 2 times 2 times 2, 5, 6, 7, 8. And that turns out to be 256. So there's 256 different combinations in one byte. Okay, so this is kind of the only major mathy formula you're going to need to know all semester. So I call it the awesome formula of doom. 2 to the number of bits you have equals the number of combinations you can make. Okay, so 2 times 2 times 2 times 2 times how many 2's you have tells you how many combinations you can make. Okay, in reverse, the doom of formula awesome, because it's backwards, is if I need to know how many bits to represent a number of combinations, I want to basically solve for this. I'm given this, I want to know that. Okay, and so you can say 2 to the what equals number of combinations. The math term for 2 to the what is how many combinations is log to the base 2. Remember logarithms? Log to the base 2 of number of combinations is number of bits you need. Okay, so I know you guys, you do logs a little bit in high school, but everybody hates them because they don't make a whole lot of sense. Log to the base 2 is pretty simple. It's the number of x, the number of times you need to chop x in half before you get to 1. Okay, log base 2 of 256 is going to be 8 because 256 divided by 2 is 128. 128 divided by 2 is 64. 64 divided by 2, see, I keep chopping it in half. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 8 divisions. So it equals 8. Okay, so don't get scared by the word log. All the word log means is I want to chop this thing in half over and over and over again until I get to 1, because it's the opposite of doubling over and over and over again until I get to the number. Okay, so there's, the homework I think has questions like, suppose I want a bit pattern for some number of things, 128 things. How many bits is that? Well, it's log to the base 2 of 128, or it's start dividing. 128 divided by 2 is 64. 64 divided by 2 is 32. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 7 divisions. Okay, so that's just applying the formula. Okay, so I wanted to show that to you. The last thing I want to talk to you about is thinking about negative numbers. So I have 8 bits, let's say. I could have more, right? 8 bits has 256 combinations. By the rules that we've done so far for binary numbers, the smallest number is that, which is 0. And the biggest number is that, which turns out to be 128 plus 64, a 1 in all of these places. And you can check my math. That's going to come out to 255 because 8 bits have 256 combinations, and if I start counting from 0, I end up at 255. But that means I don't have any way to do negatives. Okay. Representing negative numbers means we'll use some of the bit patterns as negatives. So instead of going from 0 to 255, we'll go from negative something to positive something, probably negative 128 to positive 127, I think it is, something like that. Okay. So the reason, so 0 to 255 is unsigned. Negative 128 to positive 127 signed. And the reason this is 128 and this is 127 is because I have an even number of combinations. 256 is even, but I only have 1 0. So if I have 256 things and I take out the 0, I have 255 things left that are kind of paired off with the pluses and minuses. But since 255 is odd, I have one thing that's paired off that doesn't have a pair. And we put on the minus on the negative side for reasons that will make sense in a minute. All right, so the algorithm for this, the process of negating numbers is called 2's complement. And I'm going to tell you right now, this algorithm does not make obvious sense, except that it happens to work. Okay, there's no good reason I can explain to you about why this makes sense the way I explained to you why the conversion between binary and decimal stuff work. This is what you do. Okay, to get the negative version of a positive bit pattern, first flip all the bits. By flips, I mean zeros become ones and ones become zeros. And then 2, add 1 to the flipped answer. And so if you're saying to yourself, hey, Sean, you cool, sexy dude, why is it that flipping bits and adding 1 makes something negative? It just does. Trust me. I'm sorry. I can explain it to you, but it's going to take me a whole day to explain it. It involves a lot of hardcore math, and I don't think you want to deal with that kind of hardcore math. So just trust me, this algorithm works. So here's how it works in action. Suppose I have this. This, if you check it, is 17. 116 and 1, 1, right? To get minus 17, I flip all the bits, and then I add 1. That's minus 17. Okay? Notice that it's also some really large positive number. I think it's 239 or something like that. If we interpret this as an unsigned positive number, right? Depending what the rules are. Okay, so remember what I said before. What is this? It depends. Okay, on what the rules are. It might be a positive unsigned number. It might be a negative 2's complement number. It depends on the rule. So I'm never going to ask you this and expect an answer that's not this unless I give you a specific way to interpret it. So I won't say what's this. I'll say what's this if I interpret these bits as unsigned. What's this if I interpret these bits as 2's complement? That kind of thing. Okay. The 2's complement process works in reverse. So if I start with where'd it go? That one. 1 1 1 0 1 1 1 1. That was my minus 17. And I want to negate it. I want to form minus 17, which ought to be 17 if this works. Then I would flip all the bits. 0001, 0000, and add 1, 0001, 0001. 17. Got it back. Okay, so negative and negative works. This is part of why this is the process, because you can negate a negated thing, get the original thing back. All right. So the last 5 minutes, the lab. So if you feel like this is going too fast, I just wanted to get this out there so you can watch the recording or remember how this in your head. The lab is going to walk you through playing around with bits and translations a lot more. Okay, so this is why I want to make sure you do the lab, and that, obviously 2 hours a week is not enough to get a whole semester done. The lab is going to do a lot more detail with a lot more of these conversions. Okay, so I just want to spend the last couple minutes on 2's complement fun facts. Fun fact 1: a negative number in 2's complement always starts with 1. A positive number always starts with 0. So what happens sometimes, people get confused, is I'll say, what is this interpreted as 2's complement? And they'll say, oh, you said 2's complement. That means I need to start flipping and adding 1. And they go flip it and they add 1 and they get negative something. But the rule is, everything, by the 2's complement interpretation rules, if you look at this bit, and if that bit's a 0, it's a regular positive number using the regular positive number process. If that bit is a 1, then it's negative, and you've got the only way to know. I guess this is fun fact too. The only way to know what decimal number a negative 2's complement number is to negate it to make it positive and turn that to decimal. In other words, if you show up, if I ask you what this is as a signed 2's complement number, the answer is I don't know. I don't know because I gotta do the negation. Oh, look at 17. 000 plus 1, 0001, and that's 17, which means that was minus 17. But there's no 2's place and 4's place and 8's place kind of thing with negatives. It just, to figure it out, you got to make the positive version and figure out what that is. Okay. Fun fact 3, 0 equals negative 0. So if I take 8 bits of 0 and I flip all the bits, and then I add 1. 1 plus 1 in binary is 2, but I can't write a 2 here. I have to write a 0, a 0 and carry the 1, 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 and now I have a 0 and I carry the 1 over here, but I only have 8 bits of space, so it kind of falls off the end of the world, kind of like how your odometer rolls over. And so I get 0 back. And so this is one of the reasons why we use 2's complement, is because 0's negation is 0, just like it is in regular math. The last fun fact is there is another number that's weird. And it's this one. So this, by our rules, starts with 1, so it's negative. And if we want to figure out what positive number it is, we flip all the bits, we add 1, 1 plus 1 is 0, carry the 1, 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 1. Hey, look, I got the exact same number back. So this is defined to be negative because it starts with 1. 128. This is the guy that doesn't have a positive pair. And so it's just a special weird artifact of 2's complement, and the fact that 0 has no match. Okay, so I know this was a lot of stuff to throw at you. There's a lot of mathy stuff to throw at you. I hope it's not too intimidating. But now you guys are ready to work on the lab and work on the homework. I very strongly suggest you work on the lab first. And I very strongly suggest you spend time early working on the lab so that you don't try to all do it like Monday. The lab makes you go to a web page and play around with automatically translating bits into binary and things like that. Use that web page to help you. You can use it on the homework too if you want, but you probably want to get in the habit of doing this translation yourself as well. If the web page does not load for you, you might get a Java security error. There's instructions on the Blackboard site for how to configure your computer to avoid the Java security error. If you can't figure out how to make that work, let me know and I will try to walk you through it. But again, that means you want to try to start soon. All right? Any questions on this? I know it's a lot of math, but I think it's not that bad once you get some practice on it. No questions. All right. Was that scary to a lot of math, or are you guys following okay? Okay. And so I'm going to post the recording. Yeah, more practice will absolutely help. I'm going to post the recording. Do come back and watch the video for parts that you want to see over again. A lot of people last year did that, and they said they found it really helpful. Hopefully the sound is working. I'm checking my OBS software, and the green arrow is still going, so hopefully. All right. So other than that, I will see you guys next Tuesday. Feel free to email me with questions. In fact, I want you to email me with questions. You're not bothering me. And give yourself time to start this early. You just make a habit of spending time kind of every day on these labs. All right? So if there's no more questions or anything, I will post the video, and I'll see you guys on Tuesday. Good luck.